Thank you very much. So I'd like to thank the organizers for giving me this opportunity to be part of this celebration of Jean-Pierre. So it's actually an honor to be here and speak here. So over the years, I've always admired Jean-Pierre's way in which he used deep analytic methods to actually prove beautiful results in algebraic geometry. So unfortunately, this talk will not have any analytic input. So maybe to bring it in line with the other talks, so one open problem would be to actually find an analytic interpretation of the invariants that I'm going to talk about. So actually, but on the other hand, so somehow the guiding object that I'll follow when discussing these invariants is one that actually appeared a lot in Jean-Pierre's work, the multiplier ideal. So let me say a little bit about the setting. And so everything that I'm going to talk about is part of a long-term project with Mihnea Popa. So today so X will be a complex, smooth algebraic variety. And I will focus on a hypersurface D inside X, which is always assumed to be reduced hypersurface. And if I want to look at the local equation, so locally will be given by some h equal to 0. Okay, so the main objects are these Hodge ideals. So this give a sequence of invariants denoted I k of D, where k is non-negative, and that measure in some way the singularities of D. In some sense, in the same way that the multiplier ideals measure singularities, right? So the more singular D is, the smaller, the deeper the ideals will be. Okay, so the first one, as I said, so the one that's classical and somehow that motivates the questions that we are looking at is the 0th one. So the 0th one is a multiplier ideal, in fact. So I0 of D is a multiplier ideal. So it's the first multiplier ideal that you can associate to a divisor, right? So, I mean, you cannot take the multiplier ideal of a divisor itself, but that's not interesting because it's just the ideal of the hypersurface. So this is the multiplier ideal associated to 1 minus epsilon times D, where epsilon is small enough. Okay, so what this means, right? So this consists of all functions g with the property, right? So usually you have g over h would be locally L2. So in this case, right, so g over f, the 1 minus epsilon is a locally L2. Right, so this is for all epsilon positive. Yes, thank you. Yeah, that's right. So yes, I'll keep making this mistake. All right. Okay, so this is the 0th guy, right? So I want to think of the higher ones as some sort of higher order multiplier ideals, if you want. Okay, so to make this a little more precise, so I usually think of this multiplier ideal from the point of view of a log resolution, or an embedded resolution. So I'll keep using this a bit later. So let me set up the notation. Right, so I want to look at an embedded resolution of D, by which I mean the following. So this will be a morphism. So I'll reserve actually F for this one. So this is a morphism from Y to X, with the property that it's an isomorphism over the complement of D. So over U, which is X minus D, and such that Y is, of course, smooth. And if I look at the inverse image of D, of which, again, I'm going to think just as a reduced object, so E is the inverse image of D reduced. So this is supposed to be a simple normal crossing divisor, right? So locally, it's cut out by a product of the coordinates. So let me remind you a little bit from this point of view how one can think about this ideal I0 of D, right? So what's straightforward to see is that if you push forward omega y, the top differential forms twisted by E, so this lies inside omega x twisted by D. And the difference is precisely given by this multiplier idea. Tensor with omega x of D. Okay, so very roughly, so the other ones, the IKs, will involve also the other sheaf of log differentials, also omega p of log E, where p is less than n. By the way, n for me will always be the dimension. So one reason why I find this very interesting is that somehow in birational geometry, you always measure singularities by using the difference between canonical divisors, maybe with this sort of shift given by the divisors. But somehow this picture brings in also the differential with log poles of lower order. Okay? All right, so now let me tell you exactly what these objects are. And the setting for this whole story is the theory of D modules, more precisely Saito's theory of mixed Hodge modules. So I certainly will not, I don't need to say too much about mixed Hodge modules, but at least let me say a little bit, review a little bit about D modules in order to put this in the proper context. So some basics of D modules. Okay, so what people usually say is that D module theory is an algebraic way of doing linear partial differential equations, right? So you don't care so much about solving the equation. Basically, you find a way to manipulate the objects algebraically, so you get interesting qualitative information about the systems. And the main character here is the sheaf of differential operators. So this is a sheaf of differential operators on X. So this is a subsheaf of the sheaf of linear operators over the complex numbers from OX to itself. All right, so it comes with a filtration. So you have a filtration given by the order of differential operators. So these are differential operators of order less or equal than k. So for example, F0, this is given just by multiplications by functions, by regular functions. And F1 is given by functions plus derivations. Okay, and in general, Fk is generated by k's products of objects in F1. Right, so this sheaf is generated as an as a ring just by OX and by derivations. Right, so then the subtlety comes from the fact that it's a non-commutative sheaf of rings. Right, so anyway, so what will be interested are D modules. So D modules. And for simplicity, I'll always stick to the case of left D modules. So these are simply left modules over the sheaf of differential operators. Okay? All right, so what are the basic examples? So first of all, this sheaf lies inside endomorphisms of OX. So X naturally on OX, right? So this is the most basic example. Of course, maybe the most basic example is dx itself, but let me not worry about that one. So another example of a classical flavor is the case when you have E and nabla, a vector bundle with integrable connection. Right, and these are precisely the ones, the D modules that are finitely generated over the structure sheaf. So the one that will be of interest for us today is the following. So it's given by localization process, right? So remember that we have this hypersurface D inside X. So what this sheaf is given by all rational functions with poles along D. Right? So this is simply the union over all M greater or equal than 1 of OX of MD. Right? So locally, I mean, the way it looks like, right, this is, you have the ring corresponding to X, and then you just localize the equation defining D. And of course, since if you have a fraction with h in the power of h in the denominator, if you apply a differential operator, you still get something such that the power in the, I mean, you have another power in the denominator of the same h. So this is preserved by differential operator. So it's naturally a D module. And in fact, I mean, maybe it seems like it's not a very exciting one, but this is, in fact, D modules related with this one were the reason why Bernstein introduced the theory of algebraic D modules at the beginning. So for example, I mean, the one that actually Bernstein looked at is a related one, which is this one times, let's say D is defined by the equation h equal to 0, h to the s, right? Where you can, so this is isomorphic with this one as an OX module, but then you can treat this one in such a way that I guess I have to put here also an s. Okay, this tells you how to differentiate with respect to s, to h to the s. So in fact, so what I want, my point is that somehow these are, in spite of their simplicities, they are interesting D modules. All right, how do you study these sort of objects? So to study a D module M, you choose also a filtration on M. Let's say, I guess I will always stick to the case where M is finitely generated over the ring of differential operators. All right, so I'll choose a filtration which I'll write like this. So it's an increasing filtration. And by filtration, I mean it's a filtration compatible with the filtration on the ring D itself, on dx. Right? So compatible with the filtration on dx. And the requirement is that it's finitely generated in the sense that if I look at the GR with respect to this filtration, so this is finitely generated over the GR of dx. Right, but the GR of dx, it's simply the symmetric algebra of the tangent sheaf. Right, so this is the symmetric algebra of the tangent sheaf. So in other words, what you get from this object is a sheaf on the cotangent bundle. Right, and then, of course, the sheaf itself depends on the choice of the filtration, but the support of the sheaf does not. You end up with an object that's called the characteristic variety, and which is a very interesting invariant of the D module M itself. Okay, so for example, one of the first theorems in the subject shows that if M is non-zero, then the support of this object, which lies in a 2n dimensional variety, in fact has dimension always greater or equal than n. And the most interesting class of D modules are the ones such that the dimension is precisely n. Right? So these are called the so-called holonomic D modules. And these satisfy very nice finiteness properties. Right? So these holonomic D modules are the ones such that the dimension of the support of this GUR Fm is equal to n. Okay, so this is, again, it's a strong finiteness property. And in fact, all the examples I have here, so 1 and 2 are trivially holonomic. So the interesting one, for example, is even this one. Because for this one, it's not at all obvious even that it's finitely generated over dx. Right? So this was one of the first things that Bernstein proved about holonomic D-modules, for that localization is, again, has this finiteness property. So in the above examples, they are all holonomic. All right, so this was all I wanted to say about D-modules in general. So now let me say a few words about these objects that appear in Saito's theory, these so-called mixed Hodge modules. All right, so first of all, how one could think about these objects. So I guess, so one intuition is that, let's see, so first of all, what's a mixed, or what is a Hodge module over the point? So that's simply a vector space with a Hodge structure. If it's mixed, then you have a mixed Hodge structure. So in the same way, then you have, right, if you have a sheaf on a variety, you can think of it as a family of vector spaces. So in the same way, I guess you can think of the Hodge module as a family of vector spaces with Hodge structures. Also, family of vector spaces with, depending on whether you are in the mixed or non-mixed Hodge structure. But of course, with singularities, right? So that's very important. Sorry? Yes, I'll say a little bit more a bit later. So this is really just some words to try to give some intuition. A slightly better way of phrasing it is that they are on some, maybe I should say, a variation, again, of Hodge structures with singularities. And again, what I mean by this, so this is closer to actually to the right definition. So it means that on some open subset, they are in fact variations of Hodge structures. And somehow the objects themselves come from compactifying such gadgets. So now let me actually say a little bit more what they are. So, okay, so they are given by some data, which is required to satisfy some complicated conditions of an inductive nature. So the objects themselves are not very complicated. So a Hodge module on X consists of, all right, first of all, you have a D module. So this is a D module. And it's required to satisfy some finiteness conditions, so it's holonomic. Also, it has something called regular singularities. All right, so a second, so remember that what you want something that looks a little bit like a Hodge structure. So, right, so the thing here is that it's more natural to work with increasing filtration rather than decreasing as usual. So what plays the role of the Hodge filtration here is a filtration in the sense that I discussed before. So it's All right, so this is a filtration on M. All right, but the thing to keep in mind, what's very important is that this is given to you. So here you don't have a choice of taking whatever filtration you want. All right, so it comes with a God-given one, and then you have, as Claire was asking, you have a Q structure, but that will not play much of a role. So let's say Q structure, so this is given by some perverse sheaf over Q, whatever that is. And then you also, strictly speaking, in order to have good properties, you also require existence of a polarization. So you don't fix it, but you want to have something like this. And the important part is that satisfies many conditions. So what I mean by many conditions is that you put some conditions regarding each hypersurface that appear in X. You want that some restrictions to this hypersurface are, again, Hodge modules in smaller dimension. So you end up with basically a system of conditions that you can almost never check in practice. All right? So it's very important when you have actually some examples that you know satisfy the conditions. And basically, the starting point is actually just one example. So this is the only example that you start with, and then via functors, you construct others. So the basic example is this one. So you have the D module is just the structure sheaf. So the filtration here is the trivial one in the sense that it's 0 up to level -1, and then for 0 is the whole thing. Right? So f -1 OX is 0, and f 0 OX is OX. And then the perverse sheaf is just the constant sheaf QX twisted by the dimension, and that's it. Okay? All right, so this plays the role, of course, of the basic object. And then you have functors. Right? So in some sense, the advantage is that now you can do Hodge theory in this sort of functorial setting. So you have these objects form some derived category, and you have push forward, pull back, exceptional, pull back, and so on. Okay? All right, so here is now, yes. F is the Hodge filtration, that's right, exactly. So, right, so one way to understand why should this be, for example, a filtration compatible with the filtration on dx is that this condition, right, so basically this means that fk dx times fl on M is contained in fk plus L times M. So this plays the role of Griffith's transversality, if you write down what it means. Yeah, that's right. So here, basically, you change the indices in the usual way to make it increasing. And then if you are in the mixed setting, you also have a weight filtration and so on. So actually, to have all the functors, you have to work in the mixed setting. All right, so this was the general introduction. So now let me move on to Hodge ideals. All right, so basically this is just one very special case of this construction when you have, so remember, so I had the complement of this hypersurface inside X. You have this inclusion. And then you simply take the push forward of the one that I had before, which is this QXH of n. All right, so for example, this is at the level of just OX modules, for example. Forget about D modules. If I push forward the structure sheaf on U to X, I simply get the localization. All right, so and the same is true at the level of D modules. So certainly here I get this D module, but then I get some filtration here. So this is the object that I'm interested in. All right, so. Oh, sorry. So before when right, so this is the one that I had before. Maybe I forgot, I'm sorry if I forgot to put the H. H stands for just for, I guess, for Hodge. So that's how you denote this object, right? So again, sorry, okay. So this was supposed to be U, I'm sorry. So, right, so this is supposed to be this OU and with all the data. Right, so this is just a basic object on U. You push it forward to X. So you get this D module with the filtration. Yes? That's right. So that's right. So the reason. All right. So the point is that I didn't want to say too much about the perverse. That's right. So I guess what Philippe is saying, right, is that where do the perverse sheaf come from, right? So the point is that if you have a holonomic D module by the de Riemann-Hilbert correspondence, by the what is it? Riemann-Hilbert correspondence, right? It corresponds to a holonomic to a perverse sheaf over the complex numbers. So that's why the perverse sheaf over Q is the Q structure. And of course, you require this to be compatible with this one. So you have to fix also an isomorphism. All right. So now what's known about these things? So Saito introduced them, and he proved some basic properties. Right, so this is Morihiko Saito, right, so who developed this whole theory. All right, so he proved that, for example, if D is smooth, then this filtration coincides with the polar the filtration. So OX of K plus 1 times D if K is non-negative. Okay, and if K is negative, then you have 0. So it's basically the only thing that one can think of in the smooth case. So now what happens in general? Okay, so in general, D might not be smooth, but I can restrict to some open subset whose complement has codimension at least 2 such that D is smooth. Now this sheaf, if I restrict it to that open subset and if I push it forward, stays the same. So this tells me that in general, I'm going to have an inclusion. Right? So this one is contained inside this one. Right? Might not be the whole thing. So then, in other words, this says that if I look at the case piece of this filtration, so this can be written as an ideal times this line bundle. So it's IK of D times OX of K plus 1 times D. All right, so these are the Hodge ideals. So again, so they really come from by comparing the filtration that you have on this D module with the polar the filtration. And Saito proved that the first one is, in fact, the multiplier ideal. Okay. So now what I would like to do in whatever time I have left is to explain a little bit of the properties that these ideals satisfy in order to give you a flavor of the story. And especially, I mean, so as a guiding thing, I want to always to keep in mind the properties of the multiplier ideals, right? And comparing with what happens for these ones. So let's look at some of these properties. All right, so first of all, of course, because of this thing over here, this tells us that that's right, exactly, this one over here. And he also noticed this one, so both. So, and also the statement that I0 is the multiplier ideal. So that was also noticed by him. All right, so first of all, as a formal consequence of the definition, we have that I0 of D is OX. Sorry, IK of D is OX for all K if D is smooth. And the first theorem says that, in fact, the converse holds. So, and in fact, you can make it rather precise. So you can say that if K is greater or equal than n minus 1 over 2, and Ik of D is the structure sheaf, then in fact D is smooth. Okay, so unlike the multiplier ideal, these ideals, at least if you go far enough, they recover the smoothness of the divisor. All right, so all the results that I'm going to talk about from now on are joined with Mihnea, so maybe I will not write down the names anymore. Okay. So again, so we have this I0 of D is the multiplier ideal of 1 minus epsilon times D. So in particular, what does it mean that I0 of D is a structure sheaf? Okay, so this is a well-known condition under the name of the fact that the pair X comma D is low canonical, or D is low canonical. Well, let me say D has low canonical singularities. So this is a very natural condition which appears in birational geometry, and I want to think of the other ones as some sort of strengthening of this condition, right? So the condition for IP of X to be equal to X for higher P's right, is some sort of stronger conditions on the singularities. Sorry, this should be D. Is a stronger conditions on the singularities. And let me state a couple of results to give you the flavor of how stronger this condition is. So first of all, one thing that's not obvious is that, in fact, for example, if I put the condition at level P, it implies the condition at level P minus 1. Maybe I'll say this as second theorem. So we have a sequence of inclusions. So I0 of D is the largest one. It contains I1 of D, and so on. Okay? All right, but in fact, what I would like a slightly more precise statement that forces, if I have something that's singular, that forces these Hodge ideals to be non-trivial. Right? So for example, this is one way in which one applies multiplier ideals. Right? So you have some condition, for example, that, I guess one applies it in both ways. Sometimes you are interested in having a trivial multiplier ideal, so you can apply a vanishing theorem just directly for the line bundle, but sometimes it's useful to actually force the multiplier ideal to vanish at some point. Right? So let me recall that. So what's the condition for the multiplier ideal? So if the multiplicity of the point X of D is larger than the dimension, then in fact this multiplier ideal I0 of D is contained in the maximal ideal, in the ideal defining the point. So what's the analog in this setting? Sorry?
Do you need really strict?
Well, the strict is because I remember that I always take 1 minus epsilon times D. That's why. All right, so theorem 3 says that if, so let's say that I have the multiplicity rex of D to be M. So I assume that it's not a smooth point. And all right, so I have a condition of a similar nature. And the condition is that M times k plus 1 is larger than n. Then, in fact, this ideal is contained in the, well, it vanishes at the point. So again, so somehow roughly the threshold, again, so for the multiplier ideal, the threshold is the dimension. So if you go to level k, the threshold is roughly n over k plus 1. So that's where something interesting happens. So in this sense, the conditional singularities that you need somehow, for example, to be trivial or not trivial somehow is much stronger, right, than for I0. And this is sharp. This is sharp, for example, for let's say for affine cones over smooth projective hypersurfaces. All right, so I should say one word about what to use in order to prove these things, because we don't really use mixed Hodge modules for this. So the point is that you can describe the ideals, or rather the pieces in the filtration, in terms of an embedded resolution. So before, when you look at multiplier ideals, you have this omega y twisted by E, and you push it forward. So here is more complicated. So what you have a whole complex. Each term of the complex involves some sheaf of differentials with log poles times the pullback of some piece in the filtration on differential operators downstairs. So you get this whole complex, which is some sort of piece in the de Rham complex, and you push it forward. Right? So you push it forward in the sense of derived categories. And then this is supported in just one cohomological degree, and that spits out these Hodge ideals. So somehow it's a bit complicated to actually compute it, to get your hands on what it is. Right? But I mean, in order to prove formal properties, you don't really need to say exactly what the ideal is. Yes, I get to that point. I'll do it right now. So in fact, but maybe I'll say one more thing before doing that. So you see, so this has some extra structures that you don't see in the case of just multiplier ideals, because this is a filtration over the sheaf of differential operators. So this tells you that there is some connection between the different levels depending on differentiation. All right, so note, since this is a filtration compatible with a filtration on dx, so what does it mean? So this means the following. So if I look at an object at the case level, so this looks like something, let's say, like u over h to the k plus 1. Right? So this is how an element in fk here looks like, where u is an element in the case Hodge ideal. Okay, so now if I apply differential operator with respect, I mean, let's say just partial derivative with respect to some xi, so this will lie in ik plus 1 over h to the k plus 2. So if I multiply by this one by h to the k plus 2, so this lies inside I k plus 1 of d for every such yield. Right, so now if you do the computation, basically what it gives you, some relation between the partial derivatives of u, partial derivatives of h, u and h, that produces elements in ik plus 1 of d. But furthermore, not only that you have this inclusion, but in fact, this guy is generated by such elements if k is large enough. Also, so moreover, the right-hand side is generated by left-hand side for k large enough. Okay, so now let me answer Seb's question. Okay, so what happens, for example, for simple normal crossings divisor? So here the situation is as simple as possible. So if D has simple normal crossings, all right, first of all, we know that the multiplier ideal of 1 minus epsilon times D is trivial. So then, in other words, you know that F0 OX of star D is OX of D. And in fact, from this point on, everything is determined by the previous level. So in other words, F1 dx times Fk OX of star D, I should have written the other side, is equal to Fk plus 1 OX of star D for all k. Okay, so basically everything is determined by what happens at level 0 in this case. And now if you write down how these generators look like, for example, so let's say if D is just a node in the plane, so xy equals 0, then in fact, for example, you see that ik of D is just the kth power of the maximal ideal. But of course, you can write down explicitly in all dimensions. Okay? All right, but then the natural question is, all right, but what can you say in general? When is the filtration determined at level k? All right, so the theorem is the following. Is that the filtration on this OX of star D is determined at level k. So again, what I mean by this is that ik plus 1 is determined by this, is generated by these elements, and so on also for ik plus 2 and so on. So if and only if, so given an embedded resolution as before, so you have y over x, you have this d here, we had e here, and f here. So the condition is that rq f lower star of omega y n minus q of log e is 0 for all q larger than k. Okay? So you see, so this is maybe the first place where you see these sheaf of differentials with log poles. So you need the higher direct images of these sheaves to vanish in this range. And let me point out that an analog of the Akizuki-Nakano theorem tells you that if the sum of these two exponents is larger than n, this is automatically 0. So this is the range, the first range in which something interesting happens. So in particular, for example, what you see immediately, right, is that if I take here q equal to n, this is always the case, right, because the fibers have dimension at most n minus 1. But in fact, you can go down one more step. So it always, so can always take, so always true for if you take k equal to n minus 2. Okay, so for example, if you are on a surface, then you know already that the situation at level 0 determines everything just by this differentiation procedure. Awesome. All right, so now let's see. So how many minutes do I get? 5, thanks. All right. Okay, but these are general properties, right? So then there are other general properties that is natural to ask. For example, there is something called restriction theorem for multiplier ideals, which tells you that it's a relation between the multiplier ideal on the ambient variety, its restriction, and the multiplier ideal of the restriction of the divisor. There is something entirely similar in this setting for Hodge ideals. Then there is an analog of the subadditivity theorem of the Mihnea and Lazarsfeld, again, holds for Hodge ideals. The proofs are different, but I mean, especially for the restriction theorem. But maybe what's more interesting to say is, right, so the reason why multiplier ideals are interesting is that they measure singularities, but also because they satisfy vanishing theorems. Right? So basically, the way you apply them is because they satisfy vanishing theorems. So let me state one vanishing theorem for these guys. So I don't know if what I'm going to state is the optimal result. So the point is that mixed Hodge modules always come with vanishing theorems. So they always satisfy some vanishing theorem, which looks like you take some sort of the RAM complex, you take some graded piece, you twist with an ample, and this has no hypercohomology in positive degrees. But the trouble is that in practice, somehow, it's hard to actually use the vanishing of hypercohomology of a complex. So what you want somehow to express it as vanishing of something that you understand. So that's why we have to make assumptions. Right? So the situation is the following. So I have, fix L, line bundle, such that the following conditions hold. All right, all right, maybe it's more enlightening to say first, what is the vanishing that I want? So we have, so what I want a generalization of Nadel vanishing, right? So I want hi on x. So what I'll have is omega x twisted with I k of d, twisted with O of k plus 1 times d, and twisted with L. So this is 0 for all positive I if you have a bunch of conditions. Okay, so first of all, let's see, when does Nadel tell you that you get vanishing, right? So k will be 0. So this is the multiplier ideal of 1 minus epsilon times d. So this here is just O of d. So essentially what you need the ampleness of L, maybe L also plus d. Right? So in this case, the first condition is similar. So I need the vanishing of L twisted by jd is ample for 0 less or equal than j less or equal than k. So this is completely natural. So the second condition is maybe a little bit less natural, but in practice, you don't mind it so much. So what it tells you is that the lower Hodge ideals are trivial. So I k minus 1 of d is equal to Ox. Again, this you don't mind very much because basically what you want to apply the theorem, the vanishing theorem, at the first level where you have something non-trivial. So basically you go up to the first level where this is not trivial. But the third one is actually unpleasant. It's so unpleasant that I cannot remember it. So, all right, so what this says is that you have hj in x and omega x and minus j twisted with some twist of L, k minus j plus 1 times d is equal to 0 for 1 less or equal than j less or equal than k. Okay, so So what's the problem here? So of course, in the case of Nadal, when k is 0, this condition does not show up. But otherwise, you need some vanishing in a range where Akizuki-Nakano does not apply, right? Because the sum of the exponents is equal to the dimension. So this does not come for free. So you need to know something a priori, right? So because of this, so our main applications are in the case when you have this for free. So for example, when X is the projective space, so it's something we applied to get constraints on the singularities that you have on hypersurfaces, or X being an abelian variety. Okay, but I'm afraid that my time is up, so let me stop here.